All right. Our second speaker is Kuang-Chen Lu, telling us about what happens when students switch functional languages. Please take it away.
Okay, thanks for introduction. And hi everyone, I'm Kuang-Chen from Brown University. And I'm going to talk about what happens when students switch languages, especially in cases where a functional language is involved. Students are usually taught multiple languages in CS curricula. So it is interesting to study what happens when people learn a subsequent language. There are a few things to consider when we study language transfer. Starting in the 80s, several authors studied students learning a second language after first one. Most recently, our co-author has written several papers on this topic, which is the direct inspiration for this work. She studies transfer between two languages, and her main finding is when the syntax and semantics are similar, there's good transfer. When the syntax is similar but the semantics is different, there's bad transfer. And when the syntax is different, there's little effect. However, none of her studies involve functional programming, which is what we explore in this talk. So we want to study the impact of syntactic difference and semantic difference. We have to choose a pair of programming languages. There is a key trade-off here. If we use a language that are already widely used, we get all the software and other materials that could be useful, but at a cost. We have no real control over the syntax or semantics and have to get lucky to find a suitable pair. In contrast, we could, of course, build custom languages that have exactly the syntax and the semantics we want, but they will not have the same level of support, which means we may accidentally be studying the supports rather than the languages themselves. But we have a lucky compromise, Pyret. The syntax of Pyret was directly inspired by Python and meant to be at least somewhat similar. They share some keywords and both use columns to indicate the start of a block. So this is a case of similar syntax, but different semantics. In contrast, Pyret was heavily modeled on the semantics of Racket, but designed to have a much more conventional syntax, a Python-like syntax. So we get a pair of language with different syntax, but similar semantics. So what did we decide to do? We set up two studies, one studying transfer from Racket to Pyret, and one from Pyret to Python. We also need to make a decision on the choice of research environment. Let me expand on what I mean. There are two natural choices of environment: in a lab setting, where we pay students to visit, and in courses, where the data are collected via assignments and exams. In lab setting, we are free to do things like randomized control trials, which control all confounders with randomness. It is hard or even impractical to do so in courses because students might talk to each other, which breaks the independence of two groups. Also, if we believe one condition is inferior, imposing that on students would be morally wrong. Lab setting, however, have lower ecological validity. Students might come for money rather than learning, so their motivation is different. In courses, tasks are designed in the context of a course, which means, for example, they can depend on earlier lectures or assignments. Lab tasks, however, have to be self-contained. Our earlier discussion about programming languages is also related to ecological validity. Researchers might want to create custom languages to control syntactic differences and semantic differences. This also breaks ecological validity because those custom languages might have less sophisticated supports. It is hard or expensive or even impossible to do a longitudinal study in a lab setting because we need to ask students to visit multiple times. In courses, although students might drop courses or enroll, especially at the beginning of a semester. The population is usually relatively stable, and we can repeatedly measure their performance via multiple assignments and exams. Last but not least, we can measure anything we care about in a lab setting. In a course, however, the measurements has better fit the course content and help students learn. We feel that it is wrong to ask students to do tasks that will only help us to do research, but not contribute enough to their own learning. So what did we decide to do? We use the course context to get the most useful data. First, let's look at what we found when students saw Pyret after having worked with Racket. Most students in this study have programming background. Their background is mostly in Java, C#, C++, or Python. Few students, if any, had functional programming experience. And these students are not familiar with the Pyret, the second language. And 87% of students are not familiar with Pyret at all. The rest, except for one, are at best slightly familiar. This slide is important because now we know their functional programming experience is from Racket rather than from somewhere else. When students saw Pyret, they had used Racket for 1 month up through recursive list processing functions and higher order functions. We asked students many questions about their intuitions with Pyret programs. The most interesting questions look like this. We present students a program and then ask them to predict the result of running this program. Note that we have an I don't know option. This way, students are not forced into one of the choices. First of all, students seem to transfer their knowledge from Racket to Pyret despite the evident syntactic differences. In particular, they have little trouble understanding the recursive list processing patterns and higher order functions, both common in Racket, but less likely to appear in students' prior experience. However, not everything was perfect. Here is an interesting, difficult question. Redefinition of a variable in the same block is not allowed in Racket, as in many functional languages. It is also not allowed in Pyret, because it has a semantics similar to Racket. However, 54% of students considered this Racket program okay, which is already a sad news. Worse still, the percentage goes up to 87% in the Pyret version. We suspect the situation in Pyret is influenced by students' prior experience in Python or other imperative languages with a similar syntax. Setting aside these outliers, what did we find? The most important finding is that, at least in this population, we see transfer happens, despite Racket being syntactically very different from Pyret. Now, let's move on to the next study. Pyret to Python. We did this study in a different student population. Only 44% of students reported having prior programming experience. However, 25% do have Python experience. Students switched to Python after 2 months of Pyret. We studied many language differences. For example, if is an expression in Pyret but a statement in Python. And Python has weird scoping rules like lifting binding from inside an if statement to a nearest function body. And Python allows redefinition of variables. Python has return statement and print and for loop, which can be confusing when combined with return and print. We got a couple of other differences that are presented in the paper, but I will omit them here. These differences are not specific to Python. These language features are common to many imperative languages, and many of them are unusual in a functional language. And we first asked students to predict program results by answering multiple choice questions, like what we did in the previous study. For most of these questions, very few students were able to give correct answers. Even students with Python background did poorly. What did we learn? So far, we have learned that students cannot interpret program. They struggle to predict Python program results. And after looking at students' responses carefully, we noticed that many of the wrong answers are related to misconceptions or misunderstanding about return. So we changed the question format. This time, students were given an expected result and were asked to explain why the program doesn't produce it. Most students gave reasonably correct answers. That is, students could provide the correct debugging suggestions. We cannot rigorously compare this question format with the previous one because students had been given lectures and assignments before these new tasks, and because the programs are different. However, given the dramatic change in the correct rate, such debugging questions might be easier than the interpreting questions. Also, debugging questions have higher ecological validity than predict the result of this program. If I ask myself why we care about whether students understand semantics, I would say I want them to write program efficiently, to read efficiently, or to debug efficiently, but not to interpret program efficiently. I'm not saying that the ability to interpret the program is worthless, but it is less similar to the task that really matter. And future work is required to figure out which kind of questions better capture the skills we want students to master. These are the programs that we use in this stage. They are all about print and return. Please spend a moment to read the code and decide answers. Okay, now let's focus on the first program. Most students correctly pointed out that one should use return instead of print. This might sound like a good news. However, if we look closely at why they think return is needed, we will find most explanations wrong. The most popular wrong answers think the value of the print expression is returned from this function, although they disagree on what the value is. Some students think the print returns none, and some students claim that a string is returned, and some students went even further off. They think the print terminates the whole program. There's a long tail of other misconceptions. Now let's focus on the second program. This program incorrectly inserts a new line between the return keyword and the expression of which the value should be returned. 90% of students correctly point out this correction to the program, and that return on its own will return none. However, some of these students make a slightly wrong statement. 7% of students think the 10x minus 10 expression, although not returned, will be evaluated. Now let's look at the last program. This program indents return incorrectly, and it will lead to a syntax error in Python. We receive a list of very diverse wrong answers. The most important observation about these answers is that many students think the top-level return is valid. This suggests students haven't recognized the connection between return statements and functions. After this round of tasks, we strongly believe that students don't understand return. They didn't realize that return is associated with function. Besides that, some response suggests that students have dynamic scope misconception. So we decided to focus on these two aspects in our final round of tasks. In the last round of tasks, which is also part of the final exam, we again ask students to predict the result of programs. We ask students to interpret these three programs, and let's focus on the first program. This program checks whether students consider top-level return is okay. And as we expected, 77% of students thought it is okay to return from the top level, which is wrong. Let's look at the second program. So this program is detecting dynamic scope misconception. And unfortunately, 20% of students have a dynamic scope misconception. Perhaps interestingly, some students say the program would be valid if S is returned from the program, from the function. Let's look at the last program. This program is a little complicated. You don't need to read the whole thing. The key point is that there is inside the for loop, we have a premature return. And only 70% of students correctly predicted the result of this program. So what did we find in this study? Students had many issues in the transition to Python. Many of them believe that Python functions return the last expression of their bodies and fail to recognize that return statement is essentially the only way to return a value from a function. And it is meaningless to return from the top level. Students also have misconception about print, scoping rules, and premature return within for loop. There are other less severe problems that we found in earlier stage, but did not follow up. You can find them in the paper. So what about transfer? Recall we mentioned our co-authors' work on transfer initially. How do our findings compare? In the Racket to Pyret case, even though the syntax is very different, we find a very high transfer. This is not quite consistent with prior findings. In the Pyret to Python case, the semantic differences do indeed cause significant problems, consistent with prior findings. However, it is less clear whether this is due to the transfer of knowledge or just the difficulty of Python, especially in confusion about printing and returning values. Clearly, a lot more work is needed in this area, especially to take into account prior student knowledge. But it also suggests that being functional by default and reflecting that in the syntax may lead to less confusing languages. And with that, I would like to end my talk. I have purposely designed to be fairly short to leave plenty of time for questions and discussions, since we know the topic tends to attend a lot of questions. So please feel free to ask in Discord or over Zoom, because we are monitoring both. Thank you.
Hi, Katie Casamento from Portland State University. So I have been teaching beginners full-time to program for the past couple years. This is a very, very interesting study and results. I think one thing that kind of jumped out at me is a lot of the things that you're seeing in the confusion in Python are things that I also frequently see students struggle with in their first language as well. Things that, and in particular, I think the issue with confusing kind of static and dynamic scoping I see very commonly in students who have been programming even in maybe C++ or Python for a couple years. So I guess I have a very broad and vague question, which is, first of all, as you mentioned at the end, it does seem like potentially a reasonable hypothesis that maybe the difference might come down to, languages like Pyret have arguably less different moving parts in their semantics than a language like Python, and it might simply be a matter of number of concepts or something. But I suppose the other part of this that I'm curious about is what do you think we can do? And I realize that is a very broad question, but as kind of educators, what do you think we could do to try to make sure that students don't make it several years into programming a language before they realize they don't understand basic features of the language? I find that students often get at least a year or two into programming the languages that we teach them before they start to notice errors and semantics on the level of lines and tokens and even individual functions. Do you think there's anything from this that suggests kind of an approach to help students be a little bit more careful and close read their programs more, if that makes sense?
Yeah, so let me make sure I understand your question. So you are saying that students often need maybe a couple of years to realize that they have misunderstanding about basic. Okay.
Yes,
Okay.
yes, exactly. That I find that students will often kind of, in my third or fourth year classes, realize that they never quite learned their first language. and I suppose.
So, can I jump in a little bit as a
Yeah.
co-author here?
Sure.
So we've actually been doing research for several years on this question. About 5-6 years ago, we actually studied student understanding of things like scoping rules. And we found that exactly what you said, even upper level students were having difficulty. Ironically, they had more difficulty in languages like Java that they programmed in extensively than in Racket, which they programmed in for one semester and forgotten all about, right? So I think part of this moving parts hypothesis is valid. These are persistent. I think Casey is being a little modest here because, in fact, his dissertation is building a tutor to help students understand exactly these kinds of concepts. And it's a very interesting tutor because it's built specifically, a lot of tutors are, I'm going to teach you something from scratch. Casey's tutor instead says, we are going to assume you have some basic programming knowledge, but we are going to take the misconceptions we have identified from the literature and from our own research and build a tutor literally around fixing those misconceptions using some techniques from like educational psychology. So that is, I think, our best answer for now. Casey, do you have a better answer than your dissertation?
Well, okay, Matt. So many of the misconceptions we study here are report I found in our group and also group in other continents and other institutions. So I think they are widespread, and yeah, I hope my dissertation can solve this problem partially.
Awesome. Sounds good. I will look forward to reading that. Thank you.
You could also drop us a note. We'd be happy to share it with you because we've got about a half dozen universities using it now. So just drop us a note and you can take a look at it for yourself, see if it's of any use.
Sounds good. Thank you. I will.
Hi, Mike Sperber, Active Group. So a lot of schools use Python as an intro language, as the first language. I don't know if they publish on their experience, but I wonder if you're aware of if there's any confusion that occurs with students there, or in other words, is the confusion about Python because of the difference between your languages and Python, or is it just plain confusing in Python?
Okay, so I guess this is related to our discussion at the end that it's unclear where those difficulties are from transfer or from the Python language itself. So for the return, I would tend to think that is Python. Okay, I think this is subtle. At least scoping issue should be something that about programming language in general. And so, Shriram, do you have some thoughts?
Yeah, I guess what I would say is, Mike, Python is basically not a critically evaluated language. It's used because people think it's the thing to use. And once they think it's the thing to use, you don't really question it, just like, Java or C++ before. There has actually been some decent research, like Amber Settle, for example, had a paper several years ago showing all kinds of confusion that students have in Python, learning Python as CS1. But, these are not results that are particularly popular in the community. So there is a bit of research, not a whole lot. It's not critically evaluated much. And when it is, it's found to be somewhat problematic. And we kind of, mosey along.
But are these misconceptions reported in that paper similar to the ones that you found?
In that paper, it's even more rudimentary because they were doing Python first, and so they were at an even more basic level. For example, indentation causes all kinds of problems, being, indentation sensitive in the language. Who'd have thought? Yeah. So actually causes problems, but we were, in fact, the design, as you can see from Casey's design, was carefully set up on paper so that it doesn't even become an issue, right? Like you don't have to wrestle with the code in the editor, which has ups and downs, but yeah.
Okay, thanks.
Hi, so I had a couple of questions about the study design, I guess. One, like you said, these are two specific languages. You're going in one direction. Have you considered going both directions to see if it's the like, I would assume going from Python to Pyret, but I haven't used Pyret, but going from Python to Pyret might be a different experience from the other way. And I'm curious as to like why you decided
Yeah.
these particular directions.
So I think generally starting from functional to imperative, we believe that would be easier. That's one thing. Also, if we want to do it if we do it in the classroom, we need to go in the order that makes sense, and that's why Pyret we have Pyret. We go from Pyret to Python rather than the other way around. And for the Racket and Pyret, I think in that case, yes, both directions would make sense because they have essentially the same syntax, the same semantics, just different surface syntax. In that case, that would make sense, and exploring the other direction would be a future work.
Okay. Sorry, go ahead.
Sorry, I was just saying, like a slightly different answer to Casey's is we were constrained by the choices that the courses we were able to make our studies in were doing. So the two courses we studied, one, they made exactly the transitions Casey showed. So we had no choice because we couldn't tell the courses, please go in the other direction. So we need to find an environment where we could go in the other direction and still get quality data. That's really the only thing preventing us.
Right, and I had a follow-up if we still have time. Yeah, not a follow-up, a related question, but when you said, you know, you're using assessments, what was the motivation for, I guess, were these like graded and were these, because I would assume I know you said you put in like an I don't know option so people wouldn't be kind of tempted to just pick one, but I would imagine if you kind of were like, you know, the correct answer gets points and I don't know is like probably not the correct, like I feel like there could have been biases there because it's a classroom setting. So did you think about that?
I think at least the first round of assessment should we did not grade the first round of the assessment because we want to tell their intuition about new language and not penalize them. But in a repeated assessment, we of course want them to treat those tasks seriously. So those things would be we will grade on those things.
Okay, thank you so much.
Last question.
Hi, Roger Burton Patel, Tufts University. Thanks for a great talk. What do you think you learned about this of the role of bridge languages, and specifically what makes an effective bridge language and what are some pitfalls of a bridge language? And I guess by bridge language, I mean something that is a transitional language, perhaps just as a teaching tool from one to another or even into a concept.
It's unclear to me that maybe bridge language is not really the best solution. If you are looking for like transition, so maybe it depends on your goal. If you are just thinking that the end language is too complicated, maybe something at language level that Shriram can talk a lot about would be the right solution. And if you are just thinking like, oh, students already know functional programming or already know imperative language, and they need to go to the other one. And I think in that case, given that syntax might be misleading, maybe you should choose a syntax that's slightly different. That's my take. And Shriram, do you want to add anything?
Yeah, I know we're almost out of time. The only thing I would add is I think designing and making these bridge languages would be an incredible amount of work. You are better off looking at the misconceptions that students have and tackling them directly. Right? There's a good amount of literature in cognitive psych about how to tackle misconceptions. We'd be better off leveraging that literature and directly tackling them than inventing yet another language because we'd still have new other issues that it would create, is my suspicion. But we're out of time. Thank you for the question.
Thank you. That's a great answer.
Thank you.